Comparing three or more population randomized block design problem. This is a non-parametric procedure. Consider the data in table 14.8. Recall the pharmaceutical firm wants to compare the reaction times of subjects under the influence of three different drugs that it produces. Apply the FRIEDMAN FR test to the data. What conclusion can you draw? Test using significant level of 5%, 0.05. That is the data. That is a block design. What is the meaning of block design? If we select our participant in this study, three different samples using randomized design, three different samples. We select 18 different people to apply this A procedure. We want to test the reaction time of each drug on each person. But because we did 18 tests, if we use 18 people instead 6, there is a disadvantage because it's possible that the effect of one drug will depend on race, diet, weight, age, culture, whatever. It's possible that other variable could affect this measurement. But because we are going to apply to the same subject these three drugs, then the other characteristic, one will be neutralized, and other factors like gender factor are neutralized. This is a powerful procedure in order that my sample are smaller because we don't need 18 people to apply the drug. We need only 6, and we use block design. That is the advantage of block design. Let's do this problem first in StatCrunch. We send this information to StatCrunch. Then in StatCrunch, we need to go to Stat and we need to go to non-parametric procedure, and let's select FRIEDMAN because it's a block design non-parametric. When we open that, this software requests my information in columns. Then I need to transform my data, all of this value in one column, all my response variable in one column. Then let's copy this information in this new column. The name of this column is reaction time, and let's identify the type of drug and the subject immediately. The type of drug for this is A, and let's copy this in all of these cells. The same thing that corresponds to the first subject, the second to the second subject, and so on. 6-1. Let's do the same with the same group of data. Let's copy all of these values below this, and that corresponds to the drug B, and let's copy Control C, Control V, and here we can copy because it's the same order here. And let's do the same with the third group of value. Let's copy all of this value below this, and that corresponds to the drug C, and let's Control copy, select all of these, and this will be Control E, and it's the same order for this subject. And again, we are now ready to use this non-parametric procedure in StatCrunch. Non-parametric FRIEDMAN, and where is my response variable is located in reaction time. Where is located my treatment, drug A, drug B, drug C, were located all of them in type of drug, and block design, all subjects were located here. Then compute, and we solve the problem in seconds, in a few times. We need to see here the p-value. If the p-value is small, reject the null. What is the null? The assumption that there is no difference between these three drugs. Actually, there is no big difference in the reaction time of these three drugs. We are going to use a FRIEDMAN test statistic, and these test statistics follow a chi-square distribution, and the expected value is 2. And you see, we got A. That implies that the null hypothesis is not true. We can reject the null hypothesis, and we support that at least one of these drugs differ from the other. That is the only thing that you need to do. You don't need to understand the mechanical inside of this procedure if you use a statistical software, but you need to show your work. You need to explain how can we obtain those numbers using formulas and tables. That is information that was sent to StatCrunch. We obtain this table in StatCrunch, and also we can do it in any other software. In this case, SPSS. You can use Minitab, you can use SAS, whatever software. You will obtain the same value, p-value, and chi-square, and the degree of freedom for the statistical software. Let's show our work. The first step is state the null and the alternative hypothesis. The null hypothesis is the population distribution of reaction time are identical for the three drugs. It's the same. Second, the alternative is the contrary. At least 2 2 of the 3 drugs have reaction time distribution that differ in location. That is my data because we cannot state any condition, or we cannot state how is the distribution of the population, the entire population. We have to use non-parametric procedure, free distribution. For that reason, we cannot work with this data. We need to work with the rank. Then let's order this value, but the difference in here is because we want to compare the reaction time for each individual, eliminating the effect of other factors. Then we need to rank the effect inside each block. Then here, what is the minimum value is this one. The second is this, and the third is this. And in the second row, the minimum value is this, the second value is this, and the third value is this. And in the third row, the minimum value is this one, the second is this one, and the third is this. In the other row, the minimum value is this, the other second value is this one, and the third is this. And for the next block, let's continue doing the same thing inside each block. We need to obtain the sum of each, the rank for the first drug, the rank obtained in the first block for all individuals, the rank for the second block, the second drug, and the rank for the third drug. Let's do that because we need to compute our test statistic, that is a FRIEDMAN test statistic. Let's work in Excel. In Excel, let's send our data to Excel. Already we rank it. We rank all my data inside each block. We can use this formula or this. This is a shortcut formula. The shortcut formula is easier. For Kruskal-Wallis, also we have a shortcut formula. It's easier than this formula, but I prefer to use this one to explain the logic. You are free to use either this or this one, but I am going to use this because I want to explain the logic. In here, we can see clearly that we are going to compare the rank in each drug with the total rank that we are expecting. And we compute this test statistic that have follow a chi-square distribution. We are expecting that there is no big difference between the rank for each drug compared with the other. We are going to compare this rank with the mean rank of all of them. We expect this difference close to 0. If we got a value far away from my degree of freedom, the degree of freedom in this case will be 2 because we have 3 drugs. Then the degree of freedom is 2. Our expected value for this test statistic is 2. But let's compute this test statistic. First, I am going to use this formula. Let's find the mean rank for each drug. First, we need to sum all of this rank. And after that, let's compute the mean, this value divided by 6 different subjects. That is the mean. Let's copy these two formula here, Control copy, Control V, and Control V. We compute already the mean rank for all 3 drugs. And let's compute the overall mean because the rank was doing inside each block. We have only 3 drugs inside each block. The mean of this rank could be computed in 3 different ways because we have only 1, 2, and 3. The mean of this is obvious, which is 2. And this is the position of the median. How can we obtain the first one plus the last one divided by 2 is equal to? Another way to obtain the value in the mean, the middle. We can sum 1 plus 3 plus 2, that is equal 6 divided by 3 values is equal to. Also, we can obtain this value adding the sum of all of this rank, 7 plus 12 plus 17, 7 plus 12 plus 17, divided in this case 18 value. In all of these cases, we will obtain 2. Then the overall mean is 2. We are going to compare the mean for each drug with 2. If one value is far away, is because there is a difference, because we are expecting no big difference between the average of each drug with respect to the overall, like this case. That is our expectation. The bigger is the difference, that indicate that one drug differs from other. And let's compute the term inside each formula. Then is equal the mean for this drug minus the overall mean. And let's do immediately in this case, let's square this quantity, raised to the second power. And if we want to copy this formula in these 2 cells, I need to fix this cell because in this cell we have the overall mean. The overall mean is this. Then I need to fix the column and the row for the overall mean because I am going to use the same overall mean to compute the value here. Let's Control C, Control V, and Control V. We already compute this term for the 3 samples. And let's compute the test statistic. The test statistic we need to multiply 12, let's open parentheses, 12 times B. B is the number of blocks. In this case, we have 6 blocks. Divided by K. K is the number of treatment. In this case, is 3 times K plus 1. In this case, is 4. We are going to multiply this, open parentheses, the sum of all of these squares. The sum of all of these squares are located here. Then plus this, plus this, plus this. And That is my test statistic. If we select any other set of 6 people and we do the same procedure and we compute the test statistic, the distribution of all of these test statistics, the distribution follow a chi-square distribution. Listen, we start in 0 always. And my expected value for this test statistic is again the degree of freedom. In this case, the degree of freedom is 2. We are expecting that this test statistic, the result is a value close to 2 or smaller than 2, close to 0. Actually, the perfect case when there is no difference between these 3 treatments, this result will be 0. And my expected value when we assume that there is no difference is a value here, under the assumption that there is no difference. But because my test statistic all here far away from my expectation, this is a good evidence to suspect that at least one of these treatments is different from the other. Can you see? Then in this case, 8.3 is far away from true. That is an indication that at least one treatment is the reaction time of one drug differ from the other. We have solved the problem. Let's write down all of this explanation. Let's return. We already stated the null and the alternative hypothesis. Then let's compute my test statistic. We have all value that we needed in our formula. We have everything. We substitute all of this value here. You need to write down. When you are showing your work, you need to write down all of this formula. If you send me this value if you paste using a snipping tool or using a snapshot, and you paste this in my Stab Lab, that will be extra credit. But you need to write down all of this. We need to compare this value with a reference value. How can we obtain my reference value? Using the table. In alpha, in this case, is 5%. The degree of freedom is 2. What is the reference value? What is the value in the table such that 5% of the test statistic fall on the right of it? Then let's go to the table. Degree of freedom, this is the chi-square distribution. This is 2 and alpha is 0.05. Then my reference value is 5.991. In this distribution, my expectation is in 5% of the cases, we are going to obtain a test statistic greater than 5.999. That is my reference value. Because my value was 8.3, we reject the null. Then because my value falls to the right, we reject the null. How can we obtain the same number using technology? Let's go to StatCrunch. In StatCrunch, go to calculator, go to Stat, go to calculator. In calculator, select chi-square calculator, and here you need to input the degree of freedom, which is 2. We want to find this reference point to compare my evidence. This is reference value, the critical value, my reference value. Then the degree of freedom, this is my reference value, critical value. The degree of freedom is 2. Here we need to input the area, the probability. The probability, this is a probability to the right of this point. Then I need to select here to the right, and here we need to click compute to obtain the number here. When we click compute, that is my reference value, 5.99 using technology instant table. Also, we can obtain the p-value. Then let's use also technology to find my p-value. Then my p-value in this case is the probability to obtain my evidence or one value more extreme than my evidence in the direction of my suspicion. Okay, then the degree of freedom, that is the p-value in this area. My evidence is 8.3. Can you see? This is 5, this is 10, is 8.3. Then the degree of freedom in this case is 2. We want to obtain the probability to obtain this value or one value more extreme. For that reason, I select this. Then 8.3 and click compute. Then that is the probability. That is the p-value. 1.015 was the same value that we obtained using the FRIEDMAN procedure. We have to reject the null because we don't expect this result. We expect one result close to 2 or smaller than 2 for any selection. 50 years ago or 100 years ago, the way that a statistician determined if the p-value is smaller than alpha using table was this. 8.33 is my evidence in this row for 2 degrees of freedom. This evidence is located between these two numbers. Then my evidence is here. And my p-value, because the p-value is the extreme area, all of these areas are alpha. Alpha is the extreme area in chi-square distribution. All of these numbers are probability to the right of this number, this critical value. The p-value, the area to the right, must be located between this area corresponding to this and this area corresponding to this area to the right. Then 0.01 is between 0.02 and 0.01. 0.015 is between these two values. And because the p-value is located here and my significant level, my reference point is 0.05, then p-value is obvious, is smaller than 5%. 100%. That is the way that statisticians use table, not technology, to determine if the p-value is smaller than alpha. In this case, p-value is smaller than alpha, then my evidence falls far away from my expectation, then I reject the null and I support the alternative that there is one drug that is different from the other. And that's it. It was really a pleasure to teach you this semester, and I wish you the best for all of. Thank you very much.